Hello and welcome to lesson 44, structure 2.2.7. We're going to be going over carbon and silicon forming covalent network structures. So we're going to describe the structures and explain the properties of silicon, silicon dioxide, and carbon's allotropes, diamond, graphite, fullerenes, and graphene. We'll talk about what an allotrope is, having the same element but different bonding structures and patterns and properties. So let's start with covalent network structures. What is that? What does that even mean? Well, these are large lattice structures, but the difference from these lattices of our ionic bonds and these large covalent structures is that they're composed of hundreds to thousands of covalently bonded atoms. So these aren't really molecules. Molecules are discrete things that are like water or maybe even hydrogen. But a covalent network structure looks more like a lattice. So it's something like we've discussed before of diamond, where each carbon is bonded to four carbons, where each carbon is bonded to four carbons, and so on and so forth. And so this is what we're talking about with a covalent network structure, not these molecules. So they act almost similarly to ionic bonds in certain ways, and we'll discuss where that comes from. Now, as we move into this, we're going to be talking about quite a few allotropes, specifically of carbon and silicon. And so first we're going to go over the ones of carbon. An allotrope, more specifically, is just alternate it forms of uh, different elements, or sorry, of the same element, but of elemental structures. So, for instance, the most common ones and the ones we're going to be going over are like diamond, oops, let's do a comma, graphite, graphene, and fullerene. Fullerene. So all of these are just carbon. They're all made of carbon and only carbon, but they all act quite differently physically and chemically, and they will be useful for different applications, which we'll discuss as well. And it's all based on the structures and how they bond. Now, one important thing about covalent network structures is that these things can kind of go on infinitely. They end because things are only so big. You don't have an infinitely large diamond or an infinitely large piece of graphite, but for all intents and purposes, they can go on infinitely. Covalent network structure should have no fixed size for it to be truly considered a covalent network. So let's start with diamond and let's discuss that a little bit. We already mentioned diamond when we were talking about electron domain geometry and molecular geometry in VESPER, but this is, again, a covalent network. And something important about it, a distinction we're going to make, is it's all carbon single bonds, and it's naturally occurring. Diamond's actually incredibly common, and it appears in the earth under heat and pressure. Carbon will turn into diamond. We can even make it synthetically, and that's used for like mining equipment and stuff to create synthetic diamond that goes on tools for its properties. Something very specific about it is its tetrahedral shape on each carbon. So we've already seen this image from a couple lessons ago, but I'll reinsert it here just so we can see it again. We notice that each carbon in the image is bonded to four others in that nice tetrahedral 109.5 degree bond angle. This is an incredibly strong arrangement of atoms. And generally, people know that diamond's incredibly strong. And it's due to these properties. And with that, it makes it very hard. Like you can use diamond to scratch almost any surface. It's very rigid. meaning it doesn't flex or bend. It's also non-conductive. When we talked about conductivity in a previous lesson, we talked about the movement of electrons or movement of charged particles, but these bonds are quite rigid and allow for no movement of electrons. No moving electrons. Of course, they move within their orbitals, but not from atom to atom. And also, in addition, it's very hard to break these bonds with heat, so we say it has a high melting point. So that pretty much describes diamond, its structure, its shape, and its properties. But what if these carbon atoms are not bonded tetrahedrally? Can we do that? And the answer is yes. That's where we get to graphene. Or actually, before graphene, let's do graphite. So graphite, most people often know that's what's in a pencil that allows it to write. And your pencil doesn't cut through the table or paper or anything. Pencils lead graphite is actually quite soft. We know it to be very soft. It's a little slippery, actually. If you take graphite and you put it on your fingers, you can slide them around. Or if you put it on the page, you can kind of wipe that graphite around the page. It's a shading technique you can use in art. So it's soft and slippery, very opposite from diamond, which is hard, rigid. It's also very conductive. We use graphite in a lot of electrochemistry that we're going to learn about in a much later section. So what's its structure? It turns out each carbon, instead of bonding to 4 carbons, will bond to 3 carbons. And it'll form this structure of rings of 6 carbons that lay flat on a surface. As we have 3 bonds, we end up with a structure that pretty much amounts to this infinitely. So like we continue to go off here, and this will just continue in all directions. So we have 3 bonds per carbon, and that would leave 1 extra electron. Carbon has 4 valence electrons, so 3 bonds with no non-bonding pairs, which creates a trigonal planar shape. We get a bond angle of 120 degrees. So you might ask, well, what happens to that extra electron? Well, it still exists around every carbon. We get this little electron just floating around. And these are actually delocalized electrons. So they float around the ring structures and they can move. And due to this creates conductivity because they can move from carbon to carbon across the chain. But the thing that conductivity, the thing that makes graphite special is this is just one sheet. And what happens is we get a layering of sheets. So we have one sheet, and then layered on top of it, we have another sheet. Layered on top of that, we have another sheet. Layered on top of that, we have another sheet, and so on, so forth. So these sheets layer. Oops, one sheet. And they get layered, and they're attracted to each other via these weak forces that we'll discuss in a moment. But this is what creates the brittleness. So they are stacked layers of carbon rings, carbon sheets, I guess, and they're held together by weak London dispersion forces. Now we're going to talk about this in 2 or 3 units or 2 or 3 videos, but basically you can think of these as just weak electrostatic attractions. Static attractions. So when you write on a page, what you're actually doing is just breaking these sheets off and leaving them behind the page. And if you have so much, you can rub it around, and that's what you end up doing. That's what you're rubbing around. You're rubbing the sheets across the page, creating areas of graphite on that page. So this is where we get our properties. Because the layers can separate, we say it's soft. Brittle wouldn't really be the right word here. And that's those delocalized electrons create that conductivity. And last but not least, these covalent bonds are still strong, so it still has a high melting point. So I'm going to use MP to denote the melting point. All right, so that moves us up to graphene, and you'll see why I wanted to do it after graphite. Graphene simply is just one layer of graphite. Going on infinitely, of course, like these covalent network structures, and I'm just going to use hexagons at this point. Oh, that last hexagon is weird. And as these hexagons go out, they continue on infinitely. And therefore, we're going to have a lot of the same properties as graphite. But because we only have one layer, it acts a little differently. First off, to get this one layer, this is synthetic. We have to physically separate the layers or grow them ourselves. So we have to either find a way to separate them or you can just make it. One of the possible ways that you can do at home is just take some tape. And if you just put tape over a pencil line, you can just kind of peel the tape off the pencil line. And what's left on the tape is usually about one layer of graphite. And you pretty much have therefore made graphene. So it's just a fun little project that you can do at home. But anyways, having that one layer does create a few properties that we can probably guess. It's still very conductive. The bond angles are still 120 degrees, and we still have a flat surface. It's still trigonal planar. We still have those delocalized electrons. But something about this too is that because we're only looking at one sheet, graphene is incredibly strong. Nope, there should be an either. Incredibly strong for its size slash mass. So it's even stronger than steel in these cases. If you were to take a sheet of steel the size of a sheet of graphene, the graphene would be about 100 times stronger. But with this property, we can then roll it into tubes. Roll into tubes, and that's what you get as carbon nanotubes, which you could spin into a silk or a string that could hold back airplanes. It would be so incredibly strong because it has these properties of graphene, but then you have added more depth and more mass and more thickness to it. So we often use carbon nanotubes in medical equipment or also electronics as they're very conductive. So graphene is just an incredibly useful tool for us to have, and we can just make it, honestly, a lot more simply than people realize. All right, so moving on to the next thing, that's fullerene. Fullerene, oops, I keep doing that. Fullerene is spelled with an E, not an I. Fullerene is also known as C60, carbon 60. And the reason for that is it's 60 carbons bonded together. So if it's 60 carbons bonded together, is it a network covalent structure? You can think about that for a moment, and we look back at our covalent network structures, and I see right here it should be hundreds to thousands. And we even mentioned there's no fixed amount. So this is not endless. This is not technically a covalent network. However, it's still incredibly cool. So for instance, fullerene has 3 carbons bonded per carbon, which is exactly like graphite and graphene. So we still expect a 120-degree bond angle. And around each carbon, we do have a trigonal planar geometry. But what makes this so special? Well, it's like graphene, but it's folded into a sphere, like a soccer ball. And I can insert an image of it in just a moment. Before I insert this image, we'll just go over its uses. Um, it's not very conductive, and we'll see why in a moment. But if the particles, while it still has those delocalized electrons, the particles are limited per molecule. Um, Particles, the electrons, are limited to each individual C60 molecule. So you can only conduct as far as the molecule's width. You wouldn't conduct from one molecule to another. And what we use it for is it's used for drug delivery in medicine. Delivery in medicine. It can bring drugs to very specific areas, so it's very good for targeted delivery. So let's take a look at these allotropes. So in this image here, we have our graphene. We have these layers each held together by these weak London dispersion forces in between the layers. If we take one sheet of it, we have our graphene. So we go from graphite to graphene. We can fold it into a nanotube, which gives incredible strength, or we can fold it into fullerene, which, like a soccer ball, has 12 pentagons with the hexagons around it, creating this rounded shape. So it's just a shape made of single two-dimensional flat shapes folded into a ball. And we do this with carbon to create our fullerene. And you'll notice here that because these electrons on it are just limited, they can just move around the ball, but they can't really move anywhere else. While when you have graphene, the electrons can travel across the entire length, like both graphene and graphite, or even in a nanotube, they can travel the full length. And these go on endlessly in all directions, which allow them to be so useful and so conductive. So that's our allotropes of carbon. What we're going to do is take a quick shift, and this is pretty much the end of the lesson, to look at covalent networks of silicon. So silicon is right under carbon on the periodic table. It also has 4 valence electrons and likes to make 4 bonds. There are 2 very specific ways that we look at silicon, and technically these are not allotropes because they come in different forms. There are different elements involved. We can either have pure silicon, which is used as like using computer chips. They're cut into thin wafers where they can act as semiconductors, or we can have silica, which is technically SiO2, which is actually an empirical formula because it's a covalent network. So this is just our base unit, our lowest set of um, subscripts. This is also known as quartz more commonly. So if you find quartz on the ground, you're looking at SiO2, silica, or silicon dioxide. And let's take a look at pure silicon. So silicon bonds the same as diamond. So when we look at a structure of silicon, what we're actually looking at is, turns out, the exact same structure, but with silicon atoms. We still have 4 bonds, or still tetrahedral. And due to this, we can figure that many of its properties should be the same as diamond. It's relatively strong, not as much as diamond, but it's still pretty strong, and it also has a high melting point. It's non-conductive in standard conditions like diamond, but there are ways to make it conductive. It is what we call a semiconductor, but we'll discuss that as well in a later section. So that's silicon, and now let's take a look at silica or SiO2. Turns out it also forms tetrahedral, also forms tetrahedral geometry, but it does it a little different. When we look at covalent networks of silicon dioxide, it does it with a little extra. So we get this weird tetrahedral or almost an expanded tetrahedral covalent network structure where we have silicon connected by oxygen, connected by silicon, connected by oxygen, connected by silicon. And we still get the same geometry, but we have a greater distance between the bonds. Due to the fact that this is still going to be a tetrahedral geometry, we still get the same properties of very strong. And you might know that if you've picked up a piece of quartz, it's strong, it's hard, it's quite brittle as well, and it has a very high melting point. So the tetrahedral structure we see in these covalent networks does give a lot of strength and a very high melting point, and it's quite common in anything that can form these four bonds. So I hope this helps you with covalent network structures, and have a great day.